So in chapter 5, we will talking about the stability of laminar flows. So the main idea for this for chapter 4, 5, and 6 is okay. So in chapter 4, we are looking about the laminar boundary layer. So and then when the velocity increase or you have a long plate and so on and so forth, so the lamina will change into turbulent boundary layer. But for turbulent boundary layer, we will learn in chapter 6. So we have a turbulent boundary layer. So and then in intermediate in the middle here. So in chapter 5, we will learn about the transition. Okay, transition means the situation where lamina turns into turbulent. And another factor, okay, another words or another aspect that relate with the transition is the stability. Okay, so here means in chapter 5, we learn about the stability and also the transition. So what is the stability in laminar boundary layer? So the idea is, for example, we have a flat plate here. So and then we have a free stream velocity here, and then the laminar boundary layer occur like this, for example. And then, for example, if you put a wire here, a strip wire here, okay, if the laminar boundary layer is stable, very, very stable, so the flow will flow overcome like this. So they will flow around the cylinder like this, and then the laminar boundary layer will keep continue. So means the existence of uh, uh, strip wire here not influence the formation of laminar boundary layer. However, but if the stability is not so good, so mean for example, if you put the wire here, so and then the laminar boundary layer will maybe flow like this. Okay, so it's like flow around cylinder and then suddenly it will change into turbulent. So if the wire strip is not there, it's not here, so maybe for example, so we have a plate here. So maybe the turbulent, this is laminar and this is turbulent, for example. So maybe the changes between laminar and turbulent will occur at this point. But if you put a strip wire here, so the turbulent will be occur a little bit earlier. Okay, so means that the stability is not so good at this point. But in some other point, for example, here, it will not change lamina into turbulent. So that's the idea of the stability. Okay, and then the transition here means that the changes between fully laminar into fully turbulent. So I hope you could read a little bit from internet. You can you can get a few ideas about the stability, about the transition. Okay. Later on in chapter 6, I will explain again about the transition. Okay, so this is a few notes that I take from the textbooks. So and then for chapter 5, I just give you the notes is simple because I think it is worth for you to know how to solve the problems according to a few equation, include the Fagner-Scan equation later on in the tutorial. Okay, so laminar flows have a fatal weakness for resistance to high Renault numbers. So here it is mean that laminar flow can change into turbulent if the Renault number become higher and higher. So and then here this is the terminology of stability, which is a physical state which could withstand a disturbance and still return to its original state. So it means that when you say some condition is stable, so it means that, for example, for condition A, so condition A is a stable one. So means that you have a very a deep curved surface like this. So and then you have a ball here. So you could give whether a small disturbance or a very hard disturbance. You could push this ball very hard. The ball keep rolling like this, keep moving like this, and finally it will remain to its original position. So mean this condition is actually is very stable. How so it doesn't matter you give any forces, any force, so the ball will remain in original position. And B here, it is totally unstable because uh, just applying a very small force here, so the ball will rolling, will go to another location, and it will never have possibility to turn back into its original position. So, and then C, we call it the neutral stability. So the neutral stability means that it's depend on the disturbance. So you give a very small disturbance, it will roll, it will move to another point. It will never back to its original location, but it will remain stable on that point now for that time. Okay. So and then we have for D here, so maybe it is stable, but it's only valid for the small disturbance. So means if you have a big force apply on this ball bearing on this ball, so the ball will move to another location and it will not return to its original position. So means that the keyword for stability is when you apply any forces, any force, so the condition will back to its normal condition. So this is the stable. So as I said, if you have a boundary layer like this one, this is laminar and then it will become turbulent. So if you put anything here, it can be a strip wire or it can be a rough surface here and so on and so forth. So the laminar boundary layer will remain on its condition. So this is the definition of the stability. And then when laminar condition change into turbulent, so they will have the transition period, so we call it as a transition. So the transition, why the transition sometimes it is very important, because for example, if we have a flat plate like this one, if you have a high Renault number here, so you will find that the laminar will change into the turbulent in very short period. However, if you have low or intermediate, so middle range Renault number, so the changes between laminar to turbulent will occur at certain period of time. So mean, for example, we have laminar here, and then it start the transition and then the turbulent. So the longer the transition period, so means that we need to calculate the all the data about the transition. Okay, that's the first idea. The second one is, okay, the transition is actually showing that okay, this area is fully laminar, and this area is fully turbulent. So, and then in transition period here, there is a percentage between laminar and turbulent. So, for example, at this area, so maybe it is 20% laminar, I'm sorry, 20% turbulent and 80% laminar. So, at this one might be 50-50. So, at this one might be 95% turbulent and 5% laminar, so on. So means that if we have a long transition region here, so it is difficult for us to determine the Renault transition. So we have a Renault transition here because in certain situation, we need to use the Renault transition to calculate the boundary layer thickness. Okay, normally in boundary layer here, the transition is actually the official numbers for the Renault transition is 5 times 10 by the power of 5. So this is the common or the representative, the common numbers, uh, the borderline between the laminar and turbulent. But sometimes in certain textbook, they will declare that 10 by the power of 5, the effect of transition or the effect of turbulent can be seen. So, and sometimes we could say that if the 10 by the power of 6, it is 100% turbulent. It must be turbulent after 10 by the power of 6. That's why we take the intermediate, the middle, the average point here, 5 times 10 by the power of 5, by the power of 5 as the representative value of Renault transition. So means that in our question, if it is not given what is the Renault transition, you may use 5 times 10 by the power of 5. So and then the Renault transition, so it is can be the common experimental is the pipe flow die experiment. So this is the common experiment to show the existence of laminar and also the turbulent. So for example, we have a pipe like this one. If the velocity is low, so mean the Renault number is low, so you could find that the dye here, so you could see the thin line of dye, a colored dye flow inside the pipe. So when you increase the velocity, so you will find that the dye here, okay, it can be seen and it start to spread on in the pipe. So you could still see the still see the ink, because the meaning when you could see the ink is because the ink is still uh, in common words, we could say like this one. So the why we could see the color of the ink here, because the molecule of ink is flow in a group like that one. So and then when the velocity increase, so the flow, the streamline is start to chaos, start to cross each other. So mean it breaks the group of this ink. So when another streamline comes in like this and so on, so mean it start to separate the group of ink. So and then the ink will a little bit separated like this, but the distance is quite uh, small. So means that because the distance is quite small, you could see the color. So suddenly, but if you keep increasing the velocity of water here, so you will find that the ink here is disappear. So disappear means that the ink is now travel uh, far away from of its member. So means you cannot see the color anymore, but the ink is there. So because we believe that the conservation of mass is fulfilled, so the amount of molecule of ink is there, but because it separate, and the distance is large between a molecule of ink, so we cannot see the color. So this is the evidence of the uh, laminar and turbulent flow. So this experiment is conducted by Renault, and then Renault will come with the idea of dimensionless called Renault number. So I think everybody know about this one. So Renault number. So in flow in pipe. So this is the flow in pipe. So the Renault number is rho VD over mu. Okay. So and then the turbulent, if the number is greater than 4,000, so the flow is fully turbulent. So if the number is less than 2,000, so we assume it is fully laminar. So the numbers between 2,000 and 4,000, so we assume it is a transition. So but we are focusing on boundary layer, so mean the flow over a flat plate. So in flow over a flat plate, the Renault number here is rho VL over mu. So which is L here is the length of the flat plate here. So the rho is the density, V is the free stream velocity, and mu is the dynamic viscosity. So for the uh, flow on flat plate like this one, so the transition means is 5 times 10 by the power of 5. So if the number is greater than 5 times 10 by the power of 5, so the flow is considered as a turbulent. So less than that, we could still assume that it is a laminar, because we assume that the percentage of turbulence that occur on in the boundary layer region is less than 50%. So this is the common assumption to about the transition, Renault number transition for flow on flat plate. So and then about this, I think you,
Doctor, please.
yeah, yes,
Now, the value of Renault number, if it's between 5 multiplied with 10 by the power of 5,
yes.
between this value and 5 multiplied with 10 with power of 6. Am I right?
Okay, pardon me again, please.
The limit, I'm asking about the limit of
Okay,
Renault number
okay. The
uh, in
limit
the
is
uh,
okay.
in the transition.
Okay, the limit, it is okay for you to take 5 times 10 by the power of 5. So if greater,
Bigger than this value, I'm sorry.
okay, what?
And the maximum,
Okay,
the limit.
okay, okay. Let me erase this first. Okay, so the limit is, okay, in research, sometimes people says that 10 by the power of 5, the turbulence, the percentage of turbulence start to occur. So might be 1%, 2%, and so on. So and then if the Renault number is 10 by the power of 6, so it is 100% turbulent. So this is the quite the strong opinion about the laminar and turbulence. So means that this is the range of transition. Okay, but sometimes transition will occur at very fast. Mean that the transition region is very small. In some calculation, we assume that the effect of the transition not will be counted. Okay, not be counted. So means that for that one, we assume that we take the average here. So we take 5 times 10 by the power of 5 is the Renault transition. Mean the just this borderline, if your numbers, your Renault number is less than 5 times 10 by the power of 5, so you could use laminar boundary layers equation. So if your Renault number is greater than 5 times 10 by the power of 5, so you need to assume that your boundary layers is turbulent. But it's depend on the question later on. If question say take 3 times 5 at 3 times 10 by the power of 5 in the transition numbers, so you need to take 3 times 10 by the power of 5.
Okay, doctor, thank you.
Okay. So this is about the observation of turbulent boundary layer. So if stable laminar flow here, so means that you will find that the observation, the image of the flow is clear. So yeah, it's occur for both for air and also for liquid, for water. That's why, for example, the simple example, if you see a waterfall, not a natural waterfall. For example, if you have a slope here, if you have a slope here, and then a water start to flow on the slope here. So at the beginning, so the water is laminar, so it's very smooth. So and then it start to have a bubble, a little bit bubble there, and then it become a very rough wave here. So we assume that this is actually the laminar flow. So this is the maybe this is the transition, and this transition TR, and this is the turbulent. So when in laminar here, you could see very clear. You could see the surface at the bottom here. But at the transition here, so you could maybe your observation, your you cannot see clearly the image of the bottom plate here, and the turbulent, you will find that there are so many bubbles, so many wave, rough, okay, and so on. So it seems that this is what this image try to tell us for laminar, stable laminar boundary layer here. So it's very clear, there is no any signal. So and then if the turbulence start to occur, so you will have the transition wave, for example. So and then you have the little bit vorticity, and so on and so forth. So I hope you could read these from the textbook, or also you could Google about the laminar and turbulent boundary layer. So this is actually how researchers make observation to approve or to validate their assumption of the Renault transition. Okay, but in these topics, we will use the Renault transition numbers that given in the question, or we make our simple assumption, which is 5 times 10 by the power of 5. Because okay, this is some you could get from the textbook. So it means that some experiments conducted by White. Okay, so and then conducted by this researcher. So you could see that the wave here may be the evidence of the turbulent boundary layers. So and then now I would like to show you a few equation that used in chapter 5. So I'm not going to explain how this equation being derived, but we are going after this we are going for a tutorial, so we could see how this equation being used, and we could solve certain problems. Okay, first is the Fagner-Scan solution. So in Fagner-Scan solution, as I said in previous class, so Fagner-Scan solution is actually the extension from the Blasius. So means the idea is Fagner-Scan use the same method of Blasius derived equation. So we will see about this derivation at last, because I hope I change a little bit the syllabus, because I think it is important for us to see the tutorial first, the mathematical calculation first, and then at the last I will start to explain how people do this and that. So including the Navier-Stokes equation, the usage of Navier-Stokes equation in Blasius, and so on. Okay, so and then so here, for example, in Blasius, they use the idea of eta. Okay, later on, I will explain about eta and so on in the last chapter of chapter 6. Okay, the eta is come from the similarity conducted by Blasius. So finally, Blasius will have the similarity of y square root u over 2 nu x. So here is not velocity, here is the kinematic viscosity. Okay. So and then that in Fagner-Scan, okay, so they use the same idea actually, but okay, they add the value here. So you have u2 nu x, but it has added m plus 1 here. So the way why Fagner-Scan add m plus 1 here, so it is not because the equation. So it is this almost all of the researcher that I listed here is actually use the idea of curve fitting. They do the experiment, they plot a lot of experimental data. For example, it has a lot of here, and then they start to make a curve here, and then they start to determine the equation for that curve. Later on, start on chapter 5 and chapter 6, you will have a very complicated equation. So that equation is actually not derived from the Navier-Stokes and so on. It is actually the curve fitting. So it's come from the original curve that they get from the experimental works. So here, by adding m plus 1 here, and then the m here is equal to beta is equal to m over m plus 1. So it is because Fagner-Scan is focusing on not a flat plate. I think I already discussed this in chapter 4. So Fagner-Scan actually it's not focusing on flat plate like Blasius. Fagner-Scan is focusing on which condition? It's focused on something like this one. So for example, you have a roof, a house roof, for example. So the flow, the airflow will flow like this one. Okay. So the effect of the angle here, okay, will change the curve. Okay, so the effect of angle here is actually by adding the m plus 1 here, and the relation of m and beta. Beta will reflect the angle. So we will see in the tutorial later on is 2m over m plus 1. So this is the idea of Fagner-Scan. So, and then I would like to say here is, okay, so if you compare Blasius equation from my previous equation, from my previous solution, you will find that in my notes that I give you in PDF, so that note is written eta is equal to y square root u over no x. There are no 2. Okay, so I hope this I hope you could read from the textbooks. So you will find that in textbook they will use that there is actually there are two versions of Blasius calculation. I'm using the one without the 2 here. Okay, the without the 2 here, and then if you compare with my notes that I given you in PDF and also notes from the textbook, you will find that in my notes I will have number 2 at my equation here. So we have 2f f prime. Okay, so I use f triple prime plus 2f and f prime. Okay, if you realize, that's why there are no 2 in the eta. But in the textbook, they write the value of equation is like this one. So that's the 2 will appear at this term. So that is the first difference. And the second difference is from my notes, you will find that I hope you still remember how to determine the delta. So the delta is 5x over square root Renault. So that we calculate from the Blasius. So the 5 here is actually comes out eta is equal to 5. And then we take the value of the table that's the Blasius table. We do the calculation and then we could get delta is 5x over the number. That this is if we take eta is equal y square root u over nu x. So we take eta is equal to 5. But if we take eta is equal y square root u over 2 nu x, like this one, okay, the eta here, if you see the table, later on I will show you, not in this topic, just I want to clarify this one, because we are using this equation later on. So in this, if you use this equation, you will find that eta is actually equal to 3.5. So, and then you go to the table, you will find that the eta is equal 3.5, and then you do the, because your calculation have 2 in these terms, so eta is 3.5, but the final answer is still delta is equal to 5x over square root Renault number. Okay, that I want to make a clarification here. It is not a typo. So I used U2 here because I'm following the textbooks. Okay, but so Blasius here. So the reason is because we in undergraduate study we talk about Blasius and we introduce the equation of without 2. Okay, so then I try to have a subset between the undergraduate topics and postgraduate topics. So that's why I'm using the same notes from the undergraduate. So, but unfortunately, there are no UTM graduate in this class. So they okay. So it might be a little bit weird to do that. Okay.
Sorry, doctor.
Yes.
Now in our test, we use the equation with or without 2, please.
So I think for chapter 5, you need to follow this one. Okay,
Yeah.
for if you are solving Blasius, it is okay for you to use my notes. Okay.
Okay.
Okay, but to solve a question about the transition, okay, please follow this equation.
Okay, doctor.
Okay,
But
okay.
in chapter 4, the notes is without 2.
Yes,
But in the tutorial, you use 2.
yes. In chapter 4, without 2.
Yeah.
In chapter 5, you have 2.
Okay, doctor.
Okay.
Another question, please,
Uh,
if you don't mind. Why the limit of integral from 0 to infinity?
Okay, later on, I will. This one.
Thank you. Yes,
This,
no, yes, this. Yes, doctor.
okay.
Yes,
Okay.
and plus yes, the same thing.
Okay. Okay. So, okay. Okay, so and then if you see the Blasius momentum here, so this is from momentum, and then we have changed into the limit is from 0 to infinity. But okay, the idea here, so we have a flat plate here. Okay, so for example, if we talking about okay, previously we learned about the Couette flow, the Poiseuille flow. So mean the flow inside a pipe or flow between two plates. So when flow between two plates, so we found that the it has limit from here and to here. It is very clear limit from this wall, the bottom wall to the upper wall. So you could say that this is equal, for example, y equal to 0 and this is y equal to h, because you have a very clear limit. But for boundary layer, that this one, so you have a boundary layer and so on and so forth. But you are still doing the integral on y-axis. So this is y-axis, but you will have a limit. The clear one is at the bottom here. So at the bottom here, you will find that, so this is y equal to 0. So it is a very clear limit. But for the here, okay, sometime you will see that y is equal to delta. Okay, so if you are doing with y, however, if you are doing with eta here, okay, so people will change it into the infinity, because so the infinity here actually, so this equation is actually at this stage, okay, at this stage, a general equation for this one is written as infinity here. But later on, I will show you in other tutorial that actually we could have a number for this limit. So this is just a very general equation. Okay, but the idea is, because at the end of this boundary layer, okay, so it is not a very clear limit. So and then normally in general equation we put an infinity to the upper limit here. So this is for now. Later on in tutorial, you will find that we will use the same equation, and then we could get these limits, because we have equation. Now it is quite difficult for me to explain. Can is that okay?
Okay, doctor. Thank you very
Okay,
much.
okay. So this is just the general notes first.
Yes, doctor. Thank you.
Okay, okay. So and then for this one, the tweet solution. So I just give here. Okay, so I hope you could screenshot the video later on, or you could get back the textbooks, and then but this equation is the final equation, because sometimes in textbook they will give you a lot of equation. So but sometimes that might be you cannot choose what equation need to be used. So I just show it here. So this is a tweet solution the Michel solution, the Wazan solution, and so on and so forth. We have the Venn Dryers and Blammer solution and Dunham solution. So all of this solution I tried, inshallah, I will show you in tutorial.